In this lesson, we're going to look at the filtration sequence or the normal operation mode. We're going to use this as our example for ladder logic, but before we jump in and start having a look at how things are working, let's have a look at how this sequence is supposed to operate. So we start here at the beginning of the flowchart, and note that this long line here, this thick line, denotes the fact that we're doing something in parallel. So there are two lines that come down from here. One is checking, are the shutdown conditions healthy? And the other is checking, the other is doing the main sequence for the filtration. So we'll start with this line here, which is the shutdown conditions. We're checking, are they healthy? If they are, then we're checking, has the operator pressed stop? If he hasn't, then the loop goes round in a circle, basically waiting for either shutdown conditions to happen or an operator to press the stop button. If either of those conditions come in, then we end up at this operation mode shutdown. We check the shutdown reason. It's either going to be that a wash is required, a fault has occurred, or it's a normal shutdown in the sense that it's reached a normal end of its filtration, or an operator has pressed the stop button, because an operator pressing the stop button is not a fault requirement. And then the main filtration sequence is when we go into filtration, we do a check to see if the water is below the fill level. If it is below the fill level, then that's a problem that we need to resolve. It's not a problem that stops us from going into filtration, but it is something that we need to manage before we can continue the sequence. So we then call a subsequence called pre-checks. We then call a pre-check for our sequence called fill. And as long as the pre-checks are okay, then we start the fill operation. If they're not okay, then we set the filter to offline mode and we raise alarms on the HMI. If the start fill operation is happening, if we start the fill operation, if that completes without error, then we continue on with the sequence. If it completes with an error or fails to complete, then we do the same action and we set the filter to offline mode. But as long as everything goes okay, then we move down to this next level, which is open inlet valve AV01. We do a check. We request that it's opening. We do a check to see if it's open first, and then we open AV01. And this is a little loop here that waits to see if the valve actually reaches its open limit. If the valve does reach its open limit, then continue. And it's not pictured here, but if we don't reach our open limit, then our manager will raise a fault for the valve. When the manager raises a fault for the valve, there's an implicit link to the shutdown conditions here, which causes the shutdown to occur. So we don't need to do anything with that other than check, have we opened? We then activate the control for MV02, which is our modulating valve that manages the filter level. And we activate that control, tell the valve to reach the target level in the filter. And once we have done that, we are then in filtration mode. And you'll notice that the line comes down to the parallel and then it checks, is the filter offline? No. And then we continue the loop around all the time. Now, in practice, the logic won't 100% represent this sequence because we're not realistically going to check, are we below the fill level every single scan? And is the valve open every single scan? We will maintain the fact that it needs to be open, but we won't physically go through every single step, every single scan. And I'll demonstrate as we go through the sequence, like how that's working. So for now, I'll just move this out the way. And let's go back to our main and have a look at what we looked at in the previous lesson. And I'll just jump online. So right now, if we have a look at our shutdown conditions and our start conditions, so this is the start here and the shutdown here. They are both managed by the same block that sits outside of the sequence. So that's this block here. And if we jump in, and again, I'll go into monitor and have a look, we can see that we have manage normal shutdown requirements. And what this is looking at is our normal shutdown requirements, the only one that we have that is considered a normal shutdown is the fact that an operator has pushed the stop button or the offline button in this case. So if an operator pushes the offline push button, we set the flag for normal shutdown required. We also reset the push button because in my programs, what I like to do is I don't have the HMI write false back to the button. I have the PLC write false to the button, so I know it's definitely been actioned. But obviously, you don't have to set things up that way. And then fault shutdowns, you can see that we have our interlock layer coming in here. So we have interlock A001_1, which is our filtration valve availability correct. So if any of our filtration valves, that includes valves that aren't actually used in this sequence, because we don't want our backflush valve open, for example, during normal filtration. If that becomes incorrect, then this will drop out. This will drop. This will come in. And which is why it's asking for a shutdown. So at the moment, our filtration valves are not in the correct position, so it's requesting a fault shutdown. Then we have I001_1, which is a filtration instrument availability correct. So again, right now, it is correct. That's a healthy signal. None of our instruments are reporting that they're faulty, that we need for our sequence. And then this one here is filter shutdown request on time. That is currently active. Now, notice that these are in different states and they're driven in different sort of signal types. So filter shutdown request on time, it's a request. So true would mean it's being requested, whereas filtration valve availability correct means true would mean it's correct. And I know this can trip some people up, and I know that not everybody agrees with this sort of notation that the comment tells you which way round the signal should be. But that is the way that I sort of ended up programming in my career and in my experience. So you will find that sometimes things are an open contact check, and sometimes things are a closed contact check, even though they both mean healthy. So that's just one of those things. You don't have to do it that way, but ultimately what's happening here is if an interlock is not in the correct state, then we call a fault shutdown. And then down here we have our OK to start. And if the start push button is pressed by the UI or the HMI or SCADA by the operator, and we're not asking for a normal shutdown and we're not asking for a fault shutdown, then we're OK to start. So effectively what we're doing is pre-checking our shutdown requirements to say, are you OK to start? And then when we look outside of the block again, we can see that OK to start comes to an interlock called filter, sequence, filtration, OK to start. And you can represent that on your SCADA then with an indicator that says you're not OK to start. There's no point in trying to start the sequence. There's something wrong. We're not OK to start. And then you can look at your alarm list and find out what interlocks are active. Or you can build an entire layer around your pre-starts to actually show you what the fault is as part of a pre-start checklist, which for big systems, definitely worth doing. It means that nobody has to ever jump in the code to find out what's wrong. You're literally told before you start the sequence. But for small stuff, you'll probably be okay with just your alarms, because we will be raising alarms for this stuff, and your signal saying you're not okay to start. We looked at this in the previous lesson, but we also raise normal shutdown required, fault shutdown required, and I didn't quite manage to line these up properly, but those two go together and those two go together. And that is what's controlling our start and stop of our sequence. But those are just the commands to start and stop. So if I bring this back up again, this is just, this signal has been activated to start here. And the shutdown requirements for normal and fault shutdown is this decision block here. Wow, it's more this section, I suppose, because the operator stop is also in there. So let's jump in and have a look at the actual sequence. So managing this in ladder, I find, is a very visual and easy way to do sequences. I know there's whole systems around it, and I know that a lot of people prefer SCL or structured text for doing sequencing. But if you don't need to make it complicated with loops and case statements and things like that, and it's quite a straightforward sequence, there's no harm in doing it in ladder. There's no major advantage to doing it in structured text. And in some cases, it's easier to graphically represent a sequence than it is to do it in a textual format. And I know there'll be a lot of people who disagree with me on that, but in my experience, that's how I feel about it. So the first thing in our sequence, and it won't really matter what language we're doing this in, but will be our sequence interrupts. So these are the things that will interrupt our sequence and cause either a shutdown or a shutdown because of a fault. So we can see that we always do the check, are you above your idle step? If a normal shutdown comes in or a fault shutdown comes in, then we tell the system we're shutting down. But we also latch in that shutting down to say, until we're back at sequence step 0, you are latched in. You can't come out of your shutdown status. And we also do the same if we start shutting down due to a fault, because that's a different pathway into the shutdown system. We also lock that in, because we have here, down here, we have if a fault shutdown is required. Remember, this is normal and fault. This one is just fault. If a fault shutdown is required, then we're shutting down due to fault. But we also have additional internal fault requirements that say if our internal interlock for sequence, filtration, filling sequence failed comes in, then that causes a shutdown due to fault. And again, this holds itself in as well. And this is required because we do have internal sequence steps that can cause a filling sequence failed, or we could do. So that interlock is provided to allow the sequence to fail itself without any outside sort of means. So our first step is our idle step. And you'll notice that something that I do a lot of is set my step number to a constant. So if I come up to the interface here and I come down to the bottom, we can see that we have constants for idle, determine start type, start fill required, wash required, start filtration, and filtration active. So you get a feel for how this system is set up in terms of sequence steps. And not only that, the numbers become irrelevant, because if we change the numbers in order to add steps in, they change automatically in the sequence. So I always leave 10 anyway, so you can slot 9 more steps in between. But if I had to slot 40 steps in, then I could quite easily change this value to 40, this one to 50, and this one to 60, and nothing changes in my program because they're actually using these symbolic values. The number doesn't matter, it's only to make it a unique number. And I find that works really, really well. And it also means that you are able to modify things nice and easily. So our first step is the idle step, where we're looking for the start sequence input to come into the project from our start stop block and say you are able to start. As long as we're not shutting down already for whatever reason, then we will move to our first proper step, which is determine start type. And this determine start type step is, if I just bring up the sequence again, is this block here, this sort of section here, which is saying, what are we doing first? Are we having to fill the system, or are we able to just go straight on and start the main part of the sequence, opening the valve? So we do a check that says, is the wash required? If it is required, then move the wash required into the sequence step. If it's not required, then as long as the wash is not required already, then as long as we're below the fill level, then we start filling. And if we're above or equal to the fill level, which is set to 0 at the moment, then we're able to start filtration. So before we do our check for water below fill level, we should actually be checking, are we required to wash? I haven't managed to put this on this diagram for whatever reason, but this was generated as a tool for this lesson, but I've missed that step out, but it is here. So when we say determine start type, if a wash is required, then we push the wash required into the sequence number. If it's not required, but our scaled value from our level is below our bespoke filtration fill level, then we ask for it to start a fill. If it's not doesn't need a wash and is also above our filtration fill level, then we can just start filtration. So let's follow the sort of logic through, and we'll have a look at where this wash required goes and what this does. So this brings us down to this step here, where we activate the interlock that says wash sequence requested from filter, and then we just sit in this state. So we're not stopping this sequence. What we're doing is making a call to another sequence that says you need to start and I need you to do a wash. We'll be able to pick that interlock up there and say we are starting a wash because of the filtration sequence, and then at the end of that wash, if it was successful, we can then say wash sequence requested from filter complete. That would turn that on and take us back to our determine start type. And when we go back to determine start type, what we'll find is that this wash is no longer required because it completed. If it failed, then we could have an input via another interlock into our shutdown system that says, shut this sequence down because I can't go any further because I need to do a wash, but that wash failed. And when we do the complete walkthrough at the end of this course, that stuff will be present and we'll be able to see how that comes together with the sort of visual graphical HMI that clearly demonstrates that stuff. But for now, I just want you to get into the mindset of using interlocks. We can call other sequences and we can also shut this main sequence that called it down. So we're not having to do anything complicated in terms of all the wash requirements have to exist in this sequence and jump to a different sub number or anything like that. We can literally just call another sequence and park this one here. And we'll come on to how that works in sort of the case of managing outputs that are common for each sequence later, because I know that's a sticking point when it comes to things like this. And to be honest, that is probably the thing that makes sequences so complicated when you have one asset that is shared among many different sequences that can be called at the same time. So let's have a look at the start fill required. If we make it here where we need to start a fill, that brings us down to the first subsequence that we'll see. And what this subsequence does is call a fill, basically. Now, the fill sequence can be operated either on its own from the HMI, where we just say the filter is offline. I want it to do a fill in preparation for me to bring it online later. Or it can be automatically called by this filtration system if we end up going down this line here. So pre-checks for fill operation. If they're okay, then call the start fill operation. And basically, the only pre-check that we have, because we're calling it from the filtration system, the only thing that we have is that the filtration system is healthy. So we're just picking up the shutdown request for the main parent sequence, which is this filtration sequence, the filter sequence here, the normal operation one that we're in right now. So if sequence step 20 becomes active and we are not shutting down, then this fill sequence becomes active. And in this fill sequence is ladder logic again. All we're doing in here is asking the inlet valve to open. It's a very, very simple and small sequence. If I come online, the enable becomes true. Sorry, I've got one more rung at the top. So this is our shutdown management, the same thing that we have like sequence interrupts, but there's no sequence interrupts for this. It's just a straight shutdown that says if any of this stuff comes in, no matter what you're doing, just jump straight to shutdown step, because it's such a simple sequence. We don't need to manage the shutdown. Just go straight to the shutdown step. If we're enabled and we're not shutting down, then we can open AV01. This requests open AV01 here, requests AV01 to open. And notice this arrangement here, which we've not seen yet. both the same step. This one maintains this as the sequence goes on because it's greater than or equal to. This one only activates what's behind it on this step. And all that's doing is saying move to the next step. But it's a very useful arrangement to keep things active after that step's completed, but also do something that is only relative to that one particular step. It's something that's very easy to achieve in ladder and can be a little bit more difficult to achieve in structured text, because in structured text you'd have to set anything that's on this line back to false as you leave the step, which is not a problem, but it can make the code a bit more busy, if you like, and a bit more to think about. So we would come down to confirm open, and as long as the input comes back and we're not shutting down, then we go to wait for fill limit, and the fill limit is literally what it sounds like. We set an output to say it's filling, and then as long as the scale value comes above the fill stop level and we're not already asking a shutdown to happen, then we complete. If the filter fill timeout timer times out after 10 minutes in this case, then we say we've failed to fill. And down here is our shutdown step that simply says request AV01 to close. And then when we get the close feedback, go to idle. And if we come right back up to the top, we'll see that the shutdown request causes shutdown step, failed to fill calls the shutdown step, and being complete calls the shutdown step. So all three endpoints of this this sequence or subsequence always calls the shutdown step, basically. When it comes to failed to fill, we'll notice that that's an output, and complete is also an output. So when we come back to our main parent sequence, we can pick up fill sequence complete, which is coming from, sorry, that's it's coming from this one here. So complete. And that then says, as long as we're still on sequence step 20, which we should be, because there's no way out of this step at all, then go back to determine start type, at which point we will no longer require a fill. So we know that we'll be above this level. So then we go to start filtration. And what I'm actually showing you here is not so much what the sequence is doing. I want you to focus a bit more on how the sequence is structured in ladder. So everything starts with a sequence step number. Sequence step number. Make sure if you're calling function blocks that you don't put it here, because then you'll lock the outputs of your function block to whatever they were when you were last on this step. Always allow your functions to actually scan, but don't run it unless you're in the sequence step that you need or want to be in. And then what we'll find is we come down to 40, start filtration, which we got to from this one here, start filtration. We open AV01. When AV01 no longer says it's closed, so as soon as it comes off of its close limit, that means there's water coming in. It might not be at a fast pace at that point, but there's water coming in. Then we can request MV02 to start opening, and we also turn on an interlock that says enable MV02 PID control. Now we'll come on to PID because it sits outside of our sequence, but again, I want you to think about the structure. We're not trying to manage MV02's position right now, nor are we trying to manage the PID or the level control or anything like that. All we're doing is enabling the control from the sequence, and we can then worry about managing that elsewhere outside of the sequence, keeping the sequence nice and simple, nice and easy to read, nice and easy to interrogate and modify in the future, because we know that if we change anything, we're not changing the functionality, the actual endpoint result. We're not changing how the PID works. We're only changing what enables the PID. And it's an important concept to get in your mind when you're developing asset-orientated stuff, because what we always want to sort of try and achieve is that the asset is containerized and all of its functionality is containerized. All of the control is containerized. And then you have links that link stuff together, things that enable other things, things that inhibit other things. But when you're making your modifications, you're not changing core control aspects. And again, notice that this is greater than or equal to, which enables all of this stuff. But here we say, as long as you're on step start filtration, then you can move on to filtration active, which brings us down to a pure status step, which is set the filter data, control statuses, filtration sequence active, at which point the sequence then halts, not faults, sorry. It then halts and just stays here. But remember, this will still be active, this will still be active, and this will still be active, which at the end of the day, our sequence, all it's doing is trying to open two valves and maintain a filter level, which if we look back at our control flowchart here, that's what we're doing. We open AV01, we check that AV01 is open, and then we control MV02 to achieve the normal operation target level. But that's not actually done in this sequence. The way that's done is by enabling that control via an interlock, and then that control can be handled elsewhere. So I appreciate that that is quite a lot to take in, and I think a lot of people, including myself, when I first sort of started out in PLCs, when you look at sequences and you're spoken to and you read up on this sort of stuff, you're immediately drawn to how is this sequence working? What is this sequence doing? As opposed to what is the structure of this sequence. Whereas what I'm trying to demonstrate here is the sort of makeup of this system. It's not so much what it's doing, it's the fact that things are compartmentalized into different areas. So we have a dedicated start and shutdown manager. We have a dedicated filter sequence manager that's just managing the bare bones sequence. It's not managing the actual opening of a valve. It's not managing the actual starting of a PID or the level control that goes alongside that PID. It's not doing any of that. All it's doing is saying, we now need to do that as part of this sequence. And the nice thing about that is if in another project, everything was exactly the same, there was no difference whatsoever, except for the fact that MV02 was not a PID or a PID controlled modulating valve. Instead, it was a proportional flow control valve. Well, nothing actually needs to change except for what happens when we turn on this interlock that says enable MV02 PID control. You change the comment there to proportional control, and then you change the end point of this outside the sequence that says, here's how the control actually happens. And it is an important thing to understand, and it probably goes outside the scope of this lesson a little bit because this lesson's supposed to just be sequences in ladder logic. But as this course goes on, and I realize I'm saying this on every lesson, but as the course goes on, you'll see all of this stuff come together in a better, more full pictured way, and hopefully appreciate where I'm coming from with this. And we'll see how this shapes up in another sequence that we're going to do for structured text, and how the principles are the same, but the layout has to be different because of the fact it's a different language. One thing that I haven't touched on just down here is the shutdown managers, the alarm shutdown managers for the alarms. So global alarm manager, filtration fault shutdown alarm manager. As soon as we see a fault situation come in, something that's causing us to shut down due to a fault, we raise the alarm. Now we have been through these already in the alarm section of the course, but this is how it's actually used. And then down here we have our shutdown sequence, which I'm not going to go through right now because we have a lesson on managing sequence shutdowns, and I've already sort of given the first half away with the whole start and stop function block. But the whole safe shutdown of the filter happens here. This is what causes that to happen. And then we have a request handler, which also is covered in its own lesson, but that makes up the full, complete ladder logic sequence structure. So I will add notes or answer questions on this particular topic because there's quite a lot going on here. If there's anything that you do need, drop a comment or find me on LinkedIn and message me on LinkedIn. I'm more than happy to provide more information on this. And if I need to, I will add it to the course, to this lesson underneath this video as well. So don't be afraid to ask for some extra help on this.